This is going to be our first of probably a couple of videos on Lewis dot diagrams. This one's just a recap of what we should remember from year 12, so level 2. And I'm going to use PCl3 as my example to go with it. But basically what a Lewis dot diagram tells us is the bonding within molecules and ions, and it also shows us the lone pairs of electrons as well. That becomes really important later. It's used to predict the shape, and therefore because it shows us the lone pairs of electrons in the bonding within the molecule, it can also be used to determine if it's a polar or a non-polar molecule. So it's sort of our first step in this little journey. As I say, we're going to start with PCl3 just so I can show you a quick way to remember how to do it, just a bit of a reminder. So the first thing that we really should be doing is looking at how many valence electrons we've got. Now, even though I've just spent a lot of time looking at the SPD notations, I want us to go back to the Bohr model with this one. Just the 288 type of bonding, type of electron configurations. And we're only looking at the valence shell, we're not looking at any other shell. So, and I'm using shell and I should say energy level, I know, but I'm saying that for this, we can go back to that older model because it works perfectly fine. Phosphorus is in group, depends on your numbering, but it's in group 15. That means it's got 5 electrons in its outermost energy level. So we do that. If you want to say it, it's 3s2, 3p3, okay? But it's 5. Chlorine is number 17, it's in group 17 as well, so it has got 7 electrons in its outermost energy level, in the 3rd energy level. So there's 3 of them. So we've got 5 plus 3 times 7 tells me how many electrons we've got. So 5 plus 21 is 26 electrons. If my Lewis structure doesn't have 26 electrons, then I've made a mistake. Okay? If it's got too many, it means I need to get rid of 4 of them and create a double bond somewhere. I'll show you an example of that in a moment. If it's got too few, it means I need to put some extra lone pairs of electrons somewhere. Okay, so that's why I need this number. It's also a way to determine if they gave you 2 possible structures, which one is correct. You just add up the electrons in them. Okay, PCl3, well 1 phosphorus and 3 chlorines infers that phosphorus is the central atom. So let's draw phosphorus first. And the way that I like to do it is I said, well, it's a molecule, so we're going to have 3 covalent bonds in there, aren't we? So let's put the chlorines on it. I also know that chlorine has to obey the octet rule. This will become important later when I tell you about things that don't. Okay? Chlorine has to obey the octet rule here because it's one of the outside atoms. So I'm going to use crosses because it's a bit easier to see on the video. You can use dots, hence the name Lewis dot diagrams, to fill in my chlorine so they obey that octet rule. Hopefully it's becoming a bit familiar to you now. A bond is equivalent to 2 electrons. It's 2 electrons being shared by both atoms. So 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Well, my quick math says that that's 24 electrons, and so I need 2 more electrons in there. So I'm going to put them around phosphorus, and I pair them up. And now I've got 2, 4, 6, 7, 8 around phosphorus. It also obeys the octet rule. So I tick off my 2 things. One is that I've got the right number of electrons, and number 2, that every atom is obeying the octet rule. Now the reason I put the octet rule last is because you're going to see in a later video that sometimes that octet rule gets broken. Okay, sometimes it's a rule, not a law. Okay, it can be broken. We don't need to know why, we just have to accept that it can be. Okay, so that's a nice easy one, PCl3. By the way, we can then be able to work out that with 3 bonding regions and 4 regions of electron density, its shape will be trigonal pyramidal, but we'll get to that later as well. Okay, another one that I want to quickly do for you is methanol, or CH2O. Okay, carbon has 4, hydrogen has 1, and oxygen has 6. So 4 plus 2 is 6, plus 6 is only 12 electrons. Not many for that number of atoms. If you see carbon, it's pretty safe to put it in the middle because it makes 4 covalent bonds, so it's a pretty safe one to put in the middle. Alright, so we'll do that. And then we'll put each hydrogen next to it because hydrogen can only have 2 electrons because it's in the first period, so therefore it's only the 1s orbital that can be involved with bonding. So that's done, and then we'll have our oxygen either above or below it. Okay, if I was to go and put in all the electrons, just leaving it like this, I've got 2, 4, 6, 7, 8, 9, 10, 11, 12. That looks pretty good. But I now need to go to my second rule. Is the octet rule being obeyed? No, it's not. The carbon's only got 2, 4, 6 around it, so this can't be correct. If I was to make it obey the octet rule, then I'd now have 2 too many electrons. I'd have 14, not 12. So instead of adding those 2 electrons at the top that I just did, I'm actually going to move 2 of these into the bonding region. I'm actually going to get rid of all of them to make it look a bit tidier as well. But then you can sort of say, hang on, but now isn't oxygen contributing too many electrons to the bonds? Well, actually, those 12 electrons are the valence electrons for all 4 atoms. They're all being involved in bonding. This electron isn't going to stay here. It's going to spend some time here, and here, and here, and here, and here. They move around as an electron cloud. So it doesn't matter which atoms contribute which electrons. That's irrelevant. So long as the total number is correct, and so long as you obey the octet rule whenever possible. There will be special examples where it can break the octet rule. Boron is a good example, where it only needs to have 6 electrons. Hydrogen is a great example, where it only needs 2. Beryllium only needs 4, that sort of thing. And then when you get up to ones like iodine, and actually phosphorus is a good example here as well, they can actually have more than 8. And you'll see that there's no possible way to put the electrons anywhere else, so they have to go there. But they can only do that if they're the central atom. But we'll get to that in a later video. Just get you to stop that one there, please.